Let's go ahead and start our next section and expand our information that we know about inequalities. And we're going to look at what we call compound inequalities. The way compound inequalities work is that we're joining two inequalities together by the words either and or or. So we have some examples here where we have the inequality of x plus 3 is less than 8, as well as x is greater than 2, joined by the word and. So that means what we're doing is we're taking both of those solution sets and we're trying to find a solution that satisfies both inequalities. We want to satisfy x plus 3 is less than 8 and x needs to be greater than 2. If we have an inequality joined by the word or, such as 2x divided by 3 is greater than or equal to 5, or negative x plus 10 is less than 7, we're trying to find a solution set that satisfies either inequality. So as long as it satisfies one of the two inequalities, then it is part of the combined solution set. So an intersection is our first type. Intersection is the set of all elements common to both sets, or all sets if we have more than one. It's denoted by this arch-looking symbol that kind of looks like an in, so you can think about intersection to kind of remember what that symbol means, in for intersection. And when we have a compound inequality, typically we'll look at and use the word and to describe an intersection. So the intersection of the two given equalities is going to be any solution that satisfies both inequalities, any parts of the solution set that is common to both of those sets of solutions. We have a little diagram here that kind of shows an example. When we have A intersecting with B, we have all the solutions in set A, and we have all the solutions in set B, and this area here is the solutions that exist in both sets. So what we're really looking at is an overlap between the two solution sets. Let's look at some just general sets, and then we'll expand this to inequalities. So we're given two sets. A is the set of x such that x is an even number greater than 0 and less than 10. And set B is just the numbers 3, 4, 5, and 6. So we want to find the intersection or the overlap between the two sets. Well, since our first set is even numbers greater than 0 and less than 10, we can look in our second set and identify even numbers that are greater than 0 and less than 10. Well, 4 is an even number between those values, as well as 6. If we think about this set and write it in roster form rather than set builder form, then we can identify all the even numbers greater than 0, 2, 4, 6, and 8. And we see that A contains the elements 4 and 6, as well as set B also contains the elements 4 and 6. So therefore, A intersection of B equals the elements 4 and 6. A value is a solution of a compound inequality formed by the word and if it is a solution to both inequalities. So given the compound inequality, x is less than or equal to 5 and x is greater than or equal to 3, we want to find the solution set of all the values that make both inequalities true. And one of the easiest ways is to visualize this and look at the graph of both of these inequalities and compare them. When we have x is less than or equal to 5 and x is greater than or equal to 3, What we do is when we stack our number lines here, we can see, well, what area do they have in common? And we see this overlap that exists between the values 3 and 5. So the solution to the compound inequality, that x has to be less than or equal to 5 and x has to be greater than or equal to 3, we find that it's all the values from 3 to 5. And we can see the corresponding intervals here, the interval notation that we can gain from each of these graphs, and identifying our solution interval notation is the values 3 to 5. When we have a compound inequality as an intersection joined by the word and, there's a couple different ways that we can look at the inequality, as well as identifying using a graph or an interval for the solution set. So we saw that when we solve the inequality, we have these two phrases joined by the word and. An intersection also has this unique compound or compact form where we can state that x is greater than or equal to 3 as well as less than or equal to 5. And so we're basically stating that x is between these two values. And then, of course, we have our interval notation for our solution set. Most often you'll be asked for interval notation, and occasionally there'll be some graphing involved as well. But I usually recommend, even if a graph is not requested, it helps to visualize what the interval will be and help in accuracy of identifying the solution set to the compound inequality. So let's go ahead and solve a few. So we'll solve both inequalities for each compound inequality just like we would with anything else. We'll add 7 to both sides. X is less than 9. We'll also solve the other inequality. So we have these two intervals, or these two inequalities. Well, let's take a look at a little graph. We're going to sketch our own to see where the overlap is, and then we will go ahead and identify what our actual solution is. So the only numbers we need are 4 and 9. We don't really need anything else. We could place 5, 6, 7, and 8 in between. Not really necessary. So first we look at x is less than 9. So we're going to have an open circle because it's not included. It's x is less than. And then we're looking at every value to the left. X is less than 9. Same thing with x is less than 4. We're going to have an open circle at x is less than 4. So let me do a different color on that. Open circle at x is less than 4, and then shade everything to the left. And we're looking at where their overlap is. Well, their overlap starts at x is less than 4. So our solution graph, we graph our solution set. All we have to graph is the inequality x is less than 4 and shade to the left. That is our solution set as a graph. Now that we have our solution set as a graph, we can also look at what the interval notation would be. So again, starting from least, since we're continuing forever in the negative direction, we start at negative infinity, and all the solutions from negative infinity until we reach 4. Parentheses because 4 is not included, and parentheses because infinity, negative infinity is not a number. So our solution as a graph, graphical solution, our interval notation, and inequality. So our compound inequality is the solution set is just the solution of x is less than 4. And we have the interval notation here as well. So we can see where our solutions are. So let's go ahead and solve a few more. We'll take a look at those. We solve this inequality. X is less than 0. We solve this inequality. X is less than or equal to negative 3. We'll sketch a little graph to kind of see where our overlap is. We need the numbers -3 and 0. So x is less than 0, and x is less than or equal to 3. So we see the overlap is at that interval. So we can graph our solution using only -3. We have a filled in circle shading everything to the left. That's our graphical solution. Interval notation is -infinity to -3. This time, because it's a filled in circle, because x is less than or equal to -3, and it overlaps here, we can include -3. -3 is a solution to both inequalities. And so we have our graphical solution, our interval notation, as well as the inequality solution to the compound. Let's go ahead and take another. Solve our inequality. Solve our other inequality. We have 2. So let's go ahead and sketch our graph. We have the points -2 and 0. X needs to be greater than 0, and x needs to be less than or equal to 2. Here we see there's no overlap. So there are no values that satisfy both inequalities. There's a lot of values that will satisfy either inequality, but there's no solution to the set because there's no value that satisfies both. The solution set is empty. So we have no solution. We can use our empty set symbol. We could use our empty brackets, and our number line just remains blank. Now we have a couple inequalities in compact form. So when we're dealing with compact form, normally what we do is we go ahead and think about, okay, if I just had this part here, let's ignore the rest of this for a second. To solve, I would subtract by 5, divide by -1. Don't forget to flip our inequality. So we would start by subtracting 5. But instead of just doing it to each quote-unquote side of the inequality, because we have 3 parts separated by 2 inequalities, we would do that operation to all 3 parts. So we'll cancel out the 5 there. We have -2 is less than -x, which is less than 4. Divide everything by -1. We get 2, and now we need to flip the inequality the other direction, and flip this inequality the other direction, and -4. Now, standard convention says that when we write a compact inequality, we want it to be ordered from least to greatest. So we want the smaller values on the left and the larger values on the right. Just makes it a little bit easier to kind of orient it in our minds. So we're going to flip this around as -4. Notice how this first inequality is pointing towards the -4. So when we flip it around, we need to make sure that it's pointing towards the -4. And then x. And then the second inequality is pointing away from the 2. So we need to make sure that we flip it around. So there's our compact form. Now, compact form makes graphing and interval notation pretty straightforward. We only need the numbers -4 and 2. And this inequality just states that x is between these two values of -4 and 2. Since neither of the inequalities are or equal to, they're both open circles, and we just go ahead and shade everything in between. We can write our interval starting at -4 to 2 and a parentheses on both of those. Last inequality that we're going to look at with intersections. Here we can go ahead and solve this compact inequality again. Let's go ahead and get rid of the 3, that fraction, so that we don't have to deal with that, just to make our life a little bit easier. We'll multiply everything by 3. -3 is less than or equal to. When we distribute with the first part, the first term it cancels with the denominator. And then we distribute to the 5, we get 15, less than 6. Use our same steps as before to isolate our x. So we get negative 18 is less than or equal to 2x, which is less than negative 9. Divide everything by 2. Negative 9 is less than or equal to x, which is less than negative 9 halves. You could also write that as negative 4.5. Either one is fine. We can look at our graph and say, okay, well, the only values we need are negative 9 and negative 9.5. Or I should say negative 9 halves. Negative 9 has the or equal to, so we'll actually use a filled-in circle there. But negative 9 halves is an open circle. X is between those two values. So there's our graphical solution. Our interval notation will be from negative 9 to negative 9 halves. Because it's the or equal to on the negative 9, we have a bracket, but there's no or equal to on the negative 9 halves, so we have a parentheses. So we have our compact inequality, our graph, as well as our interval notation.